class, you have learnt how to measure the temperature and the different scales of temperature. At this stage, it becomes necessary to formulate a cogent theory to explain the different heat phenomena and to see how far the proposed theory can explain the vast amount of data collected experimentally and otherwise. The experiments of Joule, Romford and Davy have shown that heat is a form of energy associated with the mechanical motion of material particles. Here I discuss first how the mechanical work is related with heat. Mechanical equivalent of heat. Work and heat both are the forms of energy. So scientist Joule developed the argument that if an amount of work or any other form of energy disappears, definite quantity of heat is produced. That is, they are related as amount of work done W is directly proportional to amount of heat produced H. That implies W equals to JH. J equals to W by H. The constant J is called the mechanical equivalent of heat. It is defined as the amount of work done to produce a unit quantity of heat. As the units of heat are calorie and joule, the value of J equals to 4.18 joule per calorie when W is measured in joule and H is measured in calorie, and J equals to 1 when both are measured in the same unit joule.
Here I am going to explain the concept of Joule's law, that is conversion of work done into heat. Here a cup of coffee is taken. Now this coffee I am pouring it into the flask. It is closed with the cap and I am shaking that. While shaking, the work done is transformed into heat. That's why when the coffee is poured into the cup, it is slightly warmed up. That you can observe. Here some smokes are coming out from it. That is, the work done is transformed into heat and absorbed by the coffee.
Calorimetry. Calorimetry deals with the measurement of heat and the quantities involved in it. Before discussing the calorimetry principle, first I discuss the factors influencing quantity of heat. The quantity of heat lost or gained by a body depends on mass and the raise or fall of the temperature of the body. Its dependence is H proportional to M and H proportional to delta T, where M equals to mass of the body and delta T equals to raise or fall of temperature. H directly proportional to M delta T. H equals to Ms delta T, where the constant S is called the specific heat of the body. It depends on the material of the body. S equals to H by M delta T.
Here two spheres of different masses are taken. Both are taken at same temperature and both made with the same material. When they are heated, the heavier mass absorbs more heat and the lighter mass absorbs less heat. That's why it expands more and that expands less. You observe it here.
It is defined as the amount of heat gained or lost by a body of unit mass to change the temperature through 1 degree Celsius. Its units are calorie per gram per Celsius in CGS system and joule per kg per Kelvin in SI system. 4200 joules per kg per Kelvin equals to 1 calorie per gram per Celsius and 1 calorie per kg kg per Kelvin. The specific heat values of few solids and liquids are: substance, specific heat in calories per gram per Celsius. Ice 0.5, lead 0.03, water 1, seawater 0.94, mercury 0.03. Therefore, from the equation H equals to ms delta T, the flow of heat from one body to another does not depend upon the amount of heat energy in them, but upon their temperatures. Now, I discussed the principle of calorimetry. When a hot body is kept in contact with a cold body, then the heat flows from hot body to cold body such that the amount of heat energy given out by the hot body is equal to the amount of heat energy received by the cold body, provided no amount of heat energy flows out into atmosphere or the surrounding medium in this process. That is, heat lost by hot body equals to heat gained by cold body. M1S1 delta T1 equals to M2S2 delta T2. The heat flows from hot body to cold body till they acquire a common temperature. That is, till a thermal equilibrium is obtained.
It is the body at higher temperature and it is the body at lower temperature. When they are kept in contact, then immediately the heat flows from the body at higher temperature to a body at lower temperature. After some time, both come to equilibrium position. When they attain the equilibrium position, the flow of heat ceases off.
Let the temperatures of hot and cold bodies be TH and TL respectively, and TE be the equilibrium temperature. Then TL less than TE less than TH, delta T1 equals to TH minus TE and delta T2 equals to TE minus TL. Calorimeter. It is used to measure the quantities of heat. It works on the principle of calorimetry. When a hot solid is mixed with water in calorimeter, then heat lost by the hot solid equals to ms1 into Th minus Te. Heat gained by the water and calorimeter equals to msw into Te minus Tl plus m-sc into Te minus Tl, where m and m' are the masses of water and calorimeter respectively. Sw and Sc are the respective specific heats. That implies S1 equals to MSW plus M-SC into Te minus Tl divided by M into Th minus Te. Using the same formula, the specific heat of a hot liquid mixed to water in calorimeter can also be determined.
It is the external structure of calorimeter, and you see this is the internal structure in which the copper vessel, stirrer and thermometer are placed. In this calorimeter, water is taken up to here and it is considered as a cold body. Now the hot piece is dropped into it and stirred with the stirrer. Then you observe temperature of the liquid raises, you see it in the thermometer. That is, according to method of mixtures, the cold body, that is water and copper calorimeter, absorb the heat, and the hot body, it loses the heat. So heat lost by the hot body is equal to heat absorbed by the cold body.
Specific heat of copper Sc equals to 0.09 CGS units. So, while determining the specific heat of a hot liquid, Sc can be neglected. Remember, specific heat of a liquid is greater than specific heat of a solid. Thus, if small m equals to capital M equals to m dash, then S1 can be written as S1 equals to SW into Te minus TH minus TE. In CGS system, SW equals to 1. S1 equals to TE minus TL divided by TH minus TE in CGS system. Under the condition, small m equals to capital M equals to M dash. Calorific value of a fuel. The heat energy produced by completely burning a unit mass of a fuel is called the calorific value or specific energy. Calorific value equals to heat produced divided by unit mass, that equals to H by M. Its units are joules per kilogram in SI system, calories per gram in CGS system. Problems. 1. Water falls from a height 500 meters. What is the raise in temperature of water at bottom if whole energy remains in water? Solution. In SI system, J equals to 1, W equals to H. Water is falling from a height H equals to 500 meters. That implies W equals to mg into 500. At the bottom, if the whole energy is converted into heat energy, then H equals to ms delta T. That implies mg into 500 equals to ms into delta T. We know G equals to 9.8 meters per second square and S of water equals to 4200 joules per kg per Kelvin in SI system. That implies M into 9.8 into 500, that equals to M into 4200 into delta T. Delta T equals to 49 by 42 equals to 1.16 degrees Celsius. How much will the temperature of 400 grams of water raised by doing 4200 joules of work in stirring the water? Solution. Given M equals to 100 grams, that equals to 0.1 kg. W equals to 4200 joules. W equals to H in SI system. W equals to ms delta T. 4200 equals to 0.1 into 4200 into delta T. That implies delta T equals to 10 degrees Celsius.